In this video, we're going to go over section 4.2 from our textbook, which talks more about polynomials and synthetic division. So we'll start here with this important theorem here. This is called the intermediate value theorem. And it says that if p of x here defines a polynomial function with only real coefficients, and if for real numbers a and b, if we were to evaluate our polynomial function at these real numbers, and the values of our polynomial at these two numbers are opposite in sign, then there exists at least one real zero within that interval between these two numbers a and b. So here is a diagram of that situation. We have our curve here, which is our polynomial function, and then here's our interval between a and b here. As you can see, if we're evaluating our function at a, and we see that this function is positive, then evaluating our function at b, we see that this function is negative. So in order for these guys to switch signs, that means it must cross the x-axis at some point, right? Because all of these are positive output values and all of these are negative output values. So in order for it to cross the x-axis, there must be at least one zero here. And we see that that's the case. P of c here at this point will give us 0. Okay. So what we'll do is look at this example here. We want to show that the polynomial function defined by this guy here has a real zero between numbers 2 and 3. Okay, so we'll do so using our intermediate value theorem. So first we're going to evaluate our function at 2 and at 3. Doing this, we'll get 2 cubed, which is 8, minus 2 times 2 squared, which is 2 times 4, which is 8, minus 2 plus 1, so we'll get minus 1. So then, p of 2 is minus 1. Now evaluating p of 3 here. We'll get 27 minus 2 times 9 minus 2. And here we'll get positive 7. So we can conclude that since p of 2 and p of 3 are opposite in sign, there is at least one zero between 2 and 3, and we'll say this is by the intermediate value theorem. Alright, so that's all we have to do for this one. We just want to show that the polynomial function has a zero between 2 and 3. Alright, so now we're going to go into synthetic division here. We're going to look at division of a polynomial by this form here. So if the degree in polynomial, where n is greater than or equal to 1, is divided by x minus k here, then the quotient polynomial, q of x, is going to have degree n minus 1. Additionally, the remainder r is going to be a constant, and it can also be 0. And the complete quotient for p of x divided by this may be written as this here. So we're dividing this polynomial by something of the form x minus k, and our answer is going to be the quotient plus our remainder over our divisor here, what we're dividing by. So we're going to do an example of, or look at an example of synthetic division here. So this is similar to polynomial long division, if you've seen it before, but it's a simpler version of that that works when we're dividing by a binomial of this form here, this x minus k. So back to this example, this is from one of the PowerPoint slides for this section. So we're going to divide this polynomial by this binomial here. So this is what it looks like, and I'm not going to go into every single step here because we'll see that in the next example, but we're dividing this guy by this binomial here, and by following the process, what we see is we get, this is our answer here. And like we said up here, our q of x, our quotient, is going to have degree n minus 1. If you look at our original polynomial, it was degree 3, and then our answer, our quotient, has degree 2. Okay. Additionally, we have this remaining amount here, 80, so our remainder is going to be 80 over what we were dividing by. What we can also do, and what we'll do throughout this video, is condense the synthetic division here by dropping our variables and just looking at the coefficients of each term here. Doing this, we see that it's a lot simpler to look at and work with. And like I said, we can still find our answer without the variables by using the fact that our quotient will have degree 1 less than our original polynomial being divided. So we can take this and write it like that. In this case, our answer is going to be 3x squared plus 9x plus 25. So I'm just looking at this here and using the fact that our answer is going to have degree 1 less than our original polynomial. And then our remainder is going to be this 80 here over the binomial we divided by. All right, so that would be our answer. This is what we get when we divide this polynomial by this. All right, so we're going to look at an example of this. So we want to divide this polynomial here by this binomial x minus 1. Okay, and before we can dive into that, here's something to note. The powers of the variables in our dividend, so the polynomial that's being divided, must be written in descending order. So we'll rewrite p of x as the following: x cubed plus 2x squared plus 0x minus 3. Okay? And we have this plus 0x to just represent the variables in descending order. Okay? And what we'll do is we'll perform synthetic division using this condensed version here. And so what we do in that case is we have to write the coefficients of each of our variables. So the coefficient of x cubed here is 1. Coefficient of 2x squared is 2. Then we have 0x, so we have a 0 here, and then a minus 3 here. So we're just looking at the coefficients, and we're dividing by, we'll look at the coefficient here, with this minus 1 here. Okay. And we can write this as the coefficient of x minus our constant term here, but throughout the book and throughout the rest of this video, we're just going to use the constant term in this binomial. All right, so here we'll work through the step-by-step process for synthetic division. The first thing that we want to do is bring down the coefficient of leading term, so the term with the highest degree, and then multiply the coefficient of this leading term by the constant in the divisor. So first, we want to bring down the coefficient of our leading term. The coefficient of our leading term is 1, so we'll bring this down. Okay. The next thing we want to do is multiply the coefficient of the leading term by the constant in the divisor. So x minus 1 is our divisor. The constant in our divisor is this minus 1 here. So we're going to multiply the coefficient of our leading term, which we know is 1, by the constant in the divisor, which is negative 1. So we'll get negative 1 here. All right, next step, what we're going to do is subtract the product in step 1, so this is our product here, from the next term in our polynomial. So we're going to subtract this, so we have this subtraction symbol, and we're going to subtract the product here from the next term in our polynomial. This is the next term. So we're going to do the next term, 2 minus our product we got, which is 1. So this becomes 2 minus minus 1. So we'll get 3 here. So that difference goes down there. The next step we're going to do is multiply the result from step 2 by the constant in the divisor. So our result from step 2 was 3 here. And we want to multiply that by the constant in the divisor. So we get negative 3 here. Okay. The next step, we want to subtract the product in step 3. So this is the product in step 3 from the next term in the polynomial. So we're going to subtract the product in step 3. So we're going to subtract negative 3 from 0. Doing so, we'll get 0 minus negative 3. So this will just be positive 3. So this result here is positive 3. In our fifth step, we want to multiply the result from step 4. So this is the result from step 4 by the constant in our divisor. So 3 times negative 1. So we'll get negative 3 here. And then we're going to subtract this product, the product we got in step 5, from the next term in our polynomial. And the next term is this minus 3. So we're doing minus 3 minus negative 3. And so in this case, we'll get minus 3 minus negative 3, which is 3, or minus 3 plus 3, so we'll get 0. So we have a 0 here. So what we see is, using the same terminology as above, this is our quotient, and this is our remainder. So the original polynomial we started with was x cubed plus 2x squared minus 3 over x minus 1. And we found that this is going to be this quotient here with degree 1 less than our original polynomial. So that means this is going to be of degree 2. And so this is going to be our coefficient of our variable with degree 2. So that'll just be 1. So we'll have x squared. This will be the coefficient of our variable with degree 1. So plus 3x. X just has to the power 1 here. And this is going to be our constant term, plus 3, right? Because we write our polynomials in decreasing order of their powers. Okay? And then we have a 0 remainder here. So this is our final answer. Okay? Now note here, this also means that this x minus 1 here is a factor of our original polynomial. And the reason being is because we can multiply this guy by this guy to get our original polynomial. All right, something else to note here, that if we were to divide by a binomial of this form here, this x plus k, we would need to rewrite it as x minus k. We need to rewrite this binomial so it has the form of x minus something. As we saw previously, we're looking at division of a polynomial by something of this form. So rewriting it, we can do the same thing, but our procedure will change slightly. When we do the 6-step procedure that we just went through here, the only thing that'll change is what we're going to do is instead add the product in the previous step for all of these guys. So that'll happen when we're dividing by a binomial of this form and rewriting it like this. So the next thing we'll look at is called the factor theorem here. So the polynomial p of x here has a factor x minus k here if and only if p of k is equal to 0. From the previous example that we just did, we saw that x minus 1 is a factor of this polynomial here, since when we did synthetic division, we divide this polynomial by this factor here, we saw that this was our answer. And so we know that x minus 1 is going to be a factor because x minus 1 times our quotient that we got is equal to our original polynomial. All right, so with that, we're going to go through this example here, we want to determine whether the second polynomial is going to be a factor of p of x here. So this guy is p of x, and then our second polynomial is this x plus 2 here. So like I mentioned before, we're looking at dividing by binomials of the form x minus k. So if we have x plus 2 here, we need to rewrite this as x minus something. So we'll rewrite this as x minus negative 2. Alright, and so doing this, our procedure will slightly change, and we'll go through that in a moment. We're going to start by writing out the coefficients of our polynomial. So we have 4, 24, 48, and 32. And we're dividing these guys by the constant in our divisor. So minus 2 here. Alright, and then remember from our procedure, the first step is to bring this coefficient down. So we have 4 here. Our next step, what we're going to do is add now, because remember we have x minus minus 2, so we're adding all of these guys. And what we're going to do is add the product of this and this guy to our second term here. So the product of 4 and minus 2 is going to be minus 8. So we're going to do 24 plus minus 8, so we'll get 16 here. The next thing we'll do is multiply this result by the constant in our divisor here. So 6 times negative 2, so we'll get negative 32 here. So we have 48 plus minus 32. This will give us, again, a positive 16. And lastly, we'll take this result here and multiply it by this guy. We get a minus 32. And then we know that 32 plus a minus 32 is going to be 0. So this tells us that our remainder is 0, and this is going to be our quotient, our q of x. So this tells us that the polynomial here divided by x plus 2 is equal to our quotient here with no remainder. And remember, our quotient is going to have degree 1 less than the polynomial we started with. And these are all of our coefficients. So we'll have 4x squared plus 16x plus 16. So this tells us that our original polynomial is equal to the quotient we got times x plus 2. This tells us that this x plus 2 is indeed a factor of our original polynomial. Right? If we can split this polynomial up into something that looks like this, we see that this is going to be a factor. So we'll conclude that x plus 2 is a factor. Something else to note here is that synthetic division will be very useful when trying to determine whether a number is a 0 of a polynomial function. For example, for this guy here, we know that if we were to let x be equal to 2, x equal to minus 2 here, that negative 2 would be a 0 for this polynomial function, because that would make this guy equal to 0. So that brings us to this next example here. We want to determine if k is equal to 2 is a 0 of this polynomial function here. So what we'll do is synthetic division. Doing our process for this, we're first going to write out the coefficients of these guys. So we have 1, minus 5, and 6. And this k here will tell us what we're going to be dividing by. Since k is positive, this is going to be x minus 2. Remember, because we're looking at a binomial of the form x minus k. If k was negative, then we would be looking at something of this form here. Alright, so we're going to divide by the the constant in that binomial term, so that'll be minus 2 here. Our first step is we're going to bring down the coefficient of our first term, so that'll be 1 here. And then we're going to be subtracting out several terms, because remember we're looking at the form of x minus 2. So with our procedure, we're going to be using subtraction. So the first thing we'll do is 1 times this minus 2 here. So we'll subtract out minus 2 from negative 5. We get negative 5 minus negative 2, which is going to be negative 3. Then we'll do negative 3 times negative 2, so that'll be positive 6. And then we'll get 6 minus 6. So we have a 0 remainder here. This tells us our q of x here is going to be x minus 3. So our original polynomial here divided by x minus 2 is going to be equal to x minus 3. Right? This tells us that this is a 0, since x minus 2 is going to be a factor of this polynomial, because we know from performing the synthetic division that x minus 2 times x minus 3, the quotient we got when performing this, is equal to our original polynomial. So it's clear from this that if k were to be equal to negative 2, this would be a 0, since plugging in 2 here into this will give us 0, and then we also see that we have another 0 here when x is going to be equal to positive 3. Alright, and then something to note here, if we did have a remainder, we would have that this would not divide our polynomial. And so we'd see that x minus k would not be a factor. And therefore, k is not a 0 in that case. But in this case, we had a 0 remainder here, so we found that this was a 0 of our polynomial function. Alrighty, and the last thing we'll look at is the remainder theorem here. So, if a polynomial is divided by this binomial here, the remainder is going to be equal to our polynomial function evaluated at this k value. So we can use the remainder theorem along with synthetic division to determine certain function values. So let's look at this example here. We're given this polynomial function, and we want to evaluate it at k is equal to negative 4. So what this means is, we're going to take our polynomial function and divide by x minus, and our k is negative 4, so it's x minus negative 4. So performing our synthetic division, we'll take the coefficients of our polynomial and divide by our k value here, so this minus 4. First thing we'll do is pull this guy down here, and we're going to add all of these guys since we have x minus minus 4. Right? So the first thing we'll do is multiply 4 by this minus 4 here. So we'll get minus 16. Negative 5 plus negative 16 is negative 21. Then we'll do negative 21 times this negative 4 here. And so we get positive 84 here. And then we'll do negative 3 plus 84. So we'll get 81. Then we'll do 81 times this negative 4, so we'll get negative 324 here. And so we'll have 2 plus negative 324, so this gives us negative 322. And so this is our remainder, and by this theorem here, the remainder is going to be equal to our polynomial function evaluated at this k value. So f evaluated at this minus 4 value. So that tells us that f evaluated at minus 4 is going to be equal to this remainder, which is negative 322. Alright, so that'll be it for this video.